By this time in our study of physics, Newton's second law has become a very familiar sight. Here it is here. It says that the net force that acts on an object is equal to the mass of that object multiplied by its acceleration. It's important, particularly right now, to appreciate that this is a vector equation, that forces are vectors, that they have not only a magnitude, but also a direction. And therefore the acceleration has a magnitude and a direction. In all the problems that we've solved, we've become familiar with appreciating the vector direction of things in order to get the right answers to our questions about the nature of motion. What this equation says fundamentally is that acceleration, which is a description of the alteration of an object's motion, is caused by forces, and that in any given situation there'll be more than one force that can cause acceleration. So the cause and effect relationship seems to be clear. Forces cause acceleration. It might surprise you to learn that this is not how Isaac Newton himself viewed Newton's second law. When he thought about the motion of objects, Isaac Newton appreciated that it wasn't just their velocity that mattered, but also their mass. And so Isaac Newton began to think about not just the acceleration, but mass and velocity together, sort of fused together in one idea that he called the quantity of motion. And it's a very, very simple idea to get your head around if you just think about some sort of everyday motions of objects. For example, this freight train. Very often freight trains don't move with a very large velocity. It's only until they get out in the open for long distances that they start going particularly fast. In a city or suburban environment, it's entirely possible that I would see a freight train moving along at only a few meters per second, 1 meter per second, 2 meters per second. A slow velocity, in fact, probably could run along next to the train and keep pace with it. So I'll tell you what I'll do. I'll get out in the tracks in front of the train and I'll put my hands out, and when the train gets there, I'll exert all of my force. And using that force, I'll change the motion of the freight train. Because Newton's second law tells me that if I apply a force, I'll cause an acceleration. Well, obviously, this is a bit silly, because what's going to happen is I'm going to get run over by the train. Because although the train has a small velocity, it has a large quantity of motion by virtue of the fact that it has a large mass. A very massive object, like a freight train, is difficult to stop, or more precisely, it's more difficult to change its motion even when it's moving slowly. And so I consider something with a very, very small mass, like this bullet, with a mass that is fantastically smaller than the mass of the freight train. And so, well, now that the mass is so small, I'll simply stand out in front of the bullet and put my hands out and stop the bullet. Again, an absurd idea. Because although the bullet has a very, very small mass, it still has a very, very large quantity of motion because it's moving with such a very high velocity. And this is the idea that Newton had in mind, that it's not just the mass that matters, or just the velocity that matters, but both at the same time. Perhaps I should try something a little bit safer, like this bumblebee. The bumblebee has a very, very tiny mass, like the bullet, less than the bullet, and travels at only a few meters per second, like the freight train. So what I'll do now, quite bravely, is I'll stand in front of the bumblebee and put my hands out and stop it. Well, now this is quite easy. Of course, I can swat a bumblebee away quite easily, because it has a small mass and it has a small velocity. It has a very, very small quantity of motion. And so when I apply a force to it, it's very, very easy to change its motion significantly and very, very rapidly. My final example is a bit of a scary one. An asteroid traveling through space has a ponderous mass. Not so big as the Earth or so big as the Moon, but enormous, like the mass of Texas, if you scoop Texas out of the ground with a big ice cream scoop. An enormous asteroid hurtling through space at a spectacular velocity. It has a tremendous quantity of motion, which is why we, those of us who are in the know, have a little bit of trepidation about the idea of the Earth being struck by an astronomical object traveling at enormous velocity through space with a large quantity of motion. I wonder if you'll recall that our discussion of the law of conservation of energy actually began with Newton's second law. Starting from Newton's second law and asking the question, how do forces change the motion of objects in space? Suddenly I derived from that kinetic energy. And by messing around with the kinetic energy and describing how forces change kinetic energy, I discovered potential energy. And among kinetic and potential energies, I discovered that there was a generalizing principle called the law of conservation of energy. That is, it's sort of like hidden inside of Newton's second law was a deeper kind of physics, a symmetry of the universe that was revealed once I practiced with it a bit and began to understand its fundamental behavior. Same thing is about to happen here. I know that Newton had in mind this idea of a quantity of motion. And so what I'm going to do is begin with Newton's second law, and from Newton's second law make a realization that there is a new symmetry that I can take advantage of to not only just to solve homework problems, but to understand my universe in a better way. And so I begin with Newton's second law. My familiar Newton's second law is that the sum of the forces is equal to mass times acceleration. I'm not putting any harpoons on the F or the A here. I want you to remember that they're there. As an experienced physics student, you know that force and acceleration are vector quantities. But here's the first step in my derivation. The acceleration that appears in Newton's second law has a definition that goes all the way back to the beginning of our study of physics. The acceleration is the change in velocity with respect to time. So I'm making that substitution here. In fact, that's the same first step that I did when I was doing the law of conservation of energy. Why would I say electron at that point? Acceleration has a specific definition. Acceleration is the rate of change of velocity. The change in velocity, like any change quantity, is the final velocity minus the initial velocity. Now I expect some eyebrows to go up here because instead of writing v minus v naught, which you might have expected, I wrote v prime minus v. This is something that's going to take a little bit of getting used to for you as a student, both in this lecture stuff and solving problems. Specifically, when we're talking about this kind of physics, we use a prime to designate the final value and unprimed to designate the initial value. It's a bit of an archaic thing that has to do with printing presses and how we might need to do subscripts. I might have one subscript in text is fine. 2 subscripts might be pushing it. 3 subscripts is impossible or was impossible to publish. And so because of that, we needed to give up on the idea of calling initial velocity, for example, sub naught, v naught, and calling the final value v prime. It's just a change in convention, a little bit of a struggle when notation changes for seemingly no reason. Hopefully you'll adapt to it easily. So the net force is equal to the mass times the acceleration is delta v over delta t, where delta v is the final velocity, v prime, minus the initial velocity, v. So that change in velocity, v prime minus v, is in parenthesis there. It's a quantity. What I'm going to do, something a little bit strange, is simply distribute the m through that quantity in the numerator. So each one of the terms gets multiplied by m, and I end up with mv prime minus mv. When I was doing conservation of energy, or the work energy theorem, I ended up with a quantity that was the difference of a term that I'd never seen before, 1/2 mv squared minus 1/2 mv naught squared, a new quantity. The same thing has happened to me here. Here in the numerator, I have a quantity, which is the mass times the velocity, specifically the mass times the final velocity, minus the mass times the initial velocity. This new quantity, mv, as it happens, is the quantity that I was looking for. So I'm going to give it a name. I'm going to call it P. The mass and the velocity conjointly, is what Isaac Newton had said. Conjointly simply means multiplied. This was the quantity of motion. Notice that the quantity mv, if the mass is large, that quantity is large. If the velocity is large, that quantity is large. It's a quantity that describes the mass and the velocity together. For want of a better symbol, we give this quantity the symbol P, and so I write Newton's second law here as the sum of the forces is equal to P prime minus P over delta T. And now I've arrived at my destination. Every change quantity, even here P prime minus P, can be represented with a delta. So when I write P final minus P initial, I can write that as delta P, the change in P. So now I have kind of a new version of Newton's second law, and actually it's a version of Newton's second law that Newton would have appreciated far better than F equals ma. It says that the sum of the forces is equal to the change in P over the change in time. Now P represents the quantity of motion. So when we think of our previous version of Newton's second law, sigma F equals ma, it sort of answers for us the question, what do forces do? Forces cause acceleration. That's what that version of it says. This version of Newton's second law, which I have to confess is completely equivalent. It says the same thing, it means the same thing, I haven't changed anything. But what it says is that it answers the question, what do forces do? They change the quantity of motion. The quantity of motion that Isaac Newton felt was a bit more important to understand, and as we'll discover, has some important fundamental natural properties of its own. I think I've done a really good job so far in holding back from giving this quantity of motion a name. Thankfully, I can breathe easy now. Delta P is the change in the momentum. This quantity of motion that I've been describing is named momentum, which once again is a familiar word in our everyday language. We've heard the term momentum before. For example, if a sports team begins a winning streak and wins several games, very often we say that they've gained momentum. And that sort of makes sense in context because it's like an irresistible quantity of motion towards the goal of perhaps winning a championship. At any rate, the quantity P, which now I've added the harpoons in again because I'm going to stress, this quantity is a vector quantity. It's really important. It's not only a magnitude, but it's also a direction. And that's not surprising because the momentum, which is the mass of a thing multiplied by its velocity, picks up the vectorness from the velocity. So momentum is mass times velocity and therefore has units of kilogram meters per second. Mass measured in kilograms, velocity in meters per second. You might imagine here that I'm going to announce that there's some sort of special unit like a momenton or something, but there really isn't. The SI unit for momentum is the kilogram meter per second. Mess around with it long enough and you'll begin to realize that a kilogram meter per second is fully equivalent to a Newton second. That's Newtons times seconds, because a Newton is a kilogram meter per second squared. If I multiply by seconds, then that becomes Newton seconds. And when I speak of momentum, you'll hear me refer to those units as Newton seconds of momentum. But it really is an advantage to the student to be aware that both of these units for momentum are common and completely equivalent. Just as the velocities of objects do not remain constant, there's acceleration all over the place, so too the momentums don't remain constant. When forces act, momentum changes. The change in momentum, delta P, gets a special name. It's called impulse. Now impulse, because it's simply the change in momentum, has the same units as delta P, Newton seconds, or same units as momentum. Newton seconds of impulse. But impulse describes the change. Now, sometimes in some textbooks, in some lectures, the impulse is given its own symbol, capital J, here with a vector sign. I don't personally do that because J with a vector sign is a symbol that I need elsewhere in my physics, and I feel it's unnecessary to conflate the two when I have a perfectly good delta p vector to stand for that. But I had to put it in here as a warning because the J is going to appear in the homework and be referred to as impulse. So I wanted to make sure that I at least gave a nod in its direction. If I need to calculate how much impulse there is in a given physical situation, there really are two ways for me to do it. If I'm given masses and velocities, I can calculate the change in momentum simply by taking the final momentum minus the initial momentum. Here, p prime minus p. If I have masses and velocities, the momenta are easy to calculate, and subtracting is easy to do, but you have to be very careful here because momentum is a vector, and I've stressed that by putting the harpoons on. Momentum can be negative. A good example would be when a pitcher is pitching a baseball toward the batter. If I choose toward the batter to be the positive direction, then as the baseball comes toward the baseball has positive momentum. But if the batter then hits the baseball changes direction. Not only does the speed of the baseball change, but the direction changes as well. The baseball in this coordinate system has positive momentum coming in and negative momentum on the way out. So when I'm calculating impulse in a problem-solving situation, sure, the definition of impulse is final minus initial, but I might find myself doing addition because momentum is a vector. Simply calculating the change in momentum by subtracting momenta is one possibility. But there's another possibility for calculating impulse, and it comes directly from Newton's second law. Newton's second law says that the sum of the forces is equal to the change in momentum divided by the change in time. A little bit of algebraic jiggery-pokery to this equation. What I discover is that the change in momentum is actually equal to, or I guess I should say also equal to, the net force multiplied by delta t. So if I'm asked to calculate impulse in a situation where I'm given forces and times, then I simply multiply the force times the time and I'll get the impulse. Examples of this would be if I'm told that a golf ball is hit from a golf tee and I want to calculate the impulse delivered to the golf ball. Well, the initial momentum of the golf ball is 0. The final momentum is unknown. So what I do, if I'm given the force, some thousands of newtons, and the time, some hundredths of seconds that the golf club is in contact with the ball, I simply multiply the force and the time, and that will give me the change in momentum. And often, knowing that change in momentum, knowing that impulse, will give me leverage to solve problems. Seeing the impulse described this way also gives me a bit of insight into physical situations that happen in everyday life. A really great example of how impulse plays a role in our lives, hopefully not our everyday lives, is in the use of airbags to protect us from injury in car accidents. Here you see a demonstration of something I think we're all sort of familiar with, a crash dummy. As a car crashes into a fixed barricade. Sensors in the car which detect acceleration activate the airbag, and the airbag deploys in front of the driver of the car at extremely high velocity. This is all happening in a fraction of a second. And as a result, the bag fully deploys before the driver's head actually comes forward and strikes the bag. Well, what good does this do us? Well, it does us a tremendous amount of good in the context of Newton's second law and impulse. The inevitable fact of a car crash is your impulse or your momentum is going to change from a velocity, some positive velocity, to 0 in a very short period of time. What the airbag does for me in a car crash is it extends the amount of time over which the momentum changes. Here on the lower right, I have my impulse equation. Delta P is equal to sigma F delta T. The delta P, as I said, is inevitable. The car is crashing. Your momentum is going to go from whatever it was to 0. The change in momentum is fixed. If I can make delta T on the right-hand side of the equation larger, that means that F will be smaller. F is the force that's actually exerted on the person. The airbag increases the distance over which the force is applied, which increases the time over which the force is applied, which requires less force. Hopefully, that amount of force, a lesser force, is insufficient to cause significant injury to the driver of the vehicle. Without an airbag, the driver's head is likely to strike the steering wheel or the dashboard or the windshield. In that collision, the time is very, very short, which causes the force to be very, very large, potentially causing significant injury. When we studied kinematics, we found that there was an advantage of making a graph of velocity as a function of time, realizing that the area under the velocity time graph was displacement. And then when we were investigating the work energy theorem, we discovered that if you make a graph of force as a function of position, that the area under the graph of force as a function of position is work. Well, the same thing is going to happen here. Since I know that a force multiplied by a certain interval of time gives me a certain impulse, delta p, I know that the area under the force as a function of time graph gives me a certain amount of impulse. For example, here on this graph, this is one of these excellent graphs that's divided up with gradation lines so I can count along. Each one of these blocks that's shown in the diagram is 1 second wide and 1 Newton high. So each block is 1 Newton second of impulse. So if I was asked what was the impulse delivered to the object from, say, 0 to 2 seconds, then I would simply add up the number of blocks. Well, from 0 to 2 seconds, I have 2 half blocks and a whole block. And so a total of 2 blocks, that's 2 Newton seconds of momentum change. And so I could say that at any time, counting up the number of blocks. Now, what this graph doesn't show me is what do I do if the graph goes below the time axis? Well, if it goes below the time axis, then that means the force has become negative, and that would mean a negative impulse. So just like displacement and just like work, signed area is the negative of the quantity. So the area under the force as a function of time graph can be calculated as impulse.